Welcome to another Papers We Love. It is September.
Yes, September. So we're getting close to the end of the year. We're a little bit I am a little bit lagging behind on announcing like the full details of the meetups that are coming up. But next month we have a visitor from the New York City chapter of Papers We Love. So she should be really, really great.
Another Greenberg.
Yes, another Greenberg. No relationship to this Greenberg that we have over here. But yes, so she's coming next month. It's going to be really nice. Try to make it if you can.
Who's doing the mini?
I don't remember.
Okay.
Yes, I forget things that I know. So
It's fine.
all right.
Administrivia.
Yes.
If you need the restroom, please just go out of this whole suite and directly to the right. Our suite door is unlocked right now, so you could just roll in. There's pizza and wine and beer on tap if you want it. Please take phone calls outside and whatnot.
We're looking for mini speakers for next year. So if you're interested in giving a topic and anything that you like from 5 to 15 minutes, come talk to me. I will get you in the calendar, and then we can help you develop your talk and everything. So it's yeah.
When is the next full-time slot available?
September of next year.
Yes.
So if you want a full one, September of next year is a thing.
You have a whole year to prepare your excellent talk for us.
It's a future you problem. So
Future you problem.
let's get started then. So as you may know, what we tend to do is introduce the speakers and with something real and something fake in their bio. So we're going to be, Stephen too is going to be speaking, and Stephen is a graduate student in EECS at UC Berkeley. Before grad school, Stephen recorded the only hit single ever made in Esperanto when he was 11. So give it up for Stephen.
Yeah.
Yes.
Hi. So I know that Inez likes to do that thing where she adds a random fact. So I only gave one fact, so it's increase the chance that you guys could guess a random fact. So it should be pretty obvious, right? Maybe. Okay. So today I'm gonna talk about random features for large-scale kernel machines. So there's a lot of words in this title, and I'm gonna try to explain them all. So this is a paper by Ali Rahimi and Ben Recht, presented in NIPS in 2007. So this is actually by CS standards, kind of an old paper, but by any other field, it's probably still pretty recent. But okay, so in order to explain what the main contribution of this paper is, we have to set up a pretty typical machine learning problem and enough background that it actually makes sense what the problem they're trying to solve. So let's start with just supervised learning. So the problem, typically, the most prototypical machine learning problem is that you get a bunch of features or data points, say from x1 to xn. So you get n of these data points, and these are just points living in some d-dimensional vector space. And you get a bunch of labels y1 to yn. And in the supervised, let's consider the case of binary classification. The labels live in, say, -1 + 1 or 0, 1. It doesn't really matter. Well, and so the typical thing you want to do is, given these data points, you want to learn a linear model so that when you see a new x, then you can actually then predict whether it belongs to, say, it's a dog or it's not a dog, or it's it's spam or not spam, or you want to be able to make predictions on new data you haven't seen. So this is kind of what's called machine learning in some sense. And the way you typically do this is you fit a linear model. So you kind of want to find, say here in the green picture, it's what's called a separating hyperplane. So the blue points here are, say, in class 1, and then the red points here are in class -1, and you want to be able to fit a plane that discriminates between the two classes. And the way you predict then is you just sort of look at which side of the boundary of the plane the new points fall on, and you say all those are +1, and the ones that live below are, say, -1. And so this is basically the most standard way you could do this. You just sort of try to minimize the square loss error, and you add a little regularization. Okay, so naturally the question is what if the data is not linear? So why do we believe in real life that data just comes in linear, and we can always just find a separating hyperplane? And so the typical solution for this is you add more dimensions until it is linear. So you almost in some sense can assume without loss of generality, that the data is linear. And the way you do this is you use some nonlinear transformation. So on the left-hand side, we see a bunch of points here. They're clearly not linearly separable because the blue circle encloses the red circle. You can't really draw a line between those two. But if I do this nonlinear feature transformation and take this two-dimensional space and put it into a three-dimensional space via this mapping at the bottom, then it clearly becomes a linearly separable problem. So I can project into a higher dimensional space, and then now I can draw a hyperplane. And then if I were to pretend take that plane and project back down to the lower dimensional space, I would essentially be able to learn that boundary between the blue and red. So this is codified or sort of made more formal in the idea of feature maps. So it's just a map that takes a lower dimensional space to a higher dimensional space. The previous example here is this nonlinear polynomial map. And the key idea here is that then we can still solve linear problems indeed in bigger dimensions, but we can still solve linear problems here. So we can take R2 to R10, and then we can solve a problem in R10, and life is good. Okay. So here's an example of using feature maps where we've been able to learn a very nonlinear decision boundary. And this is a very powerful technique that's used all the time. So naturally the question now is, what if D goes to infinity, right? So or even if what if D is really large? What if it's like a million? We don't want to learn a million. You don't want to have to do an optimization problem on a million dimensional variable. And if it's infinite, we can't really even do that because we can't even write it down in memory. So the way that this problem is handled is via the idea of kernels. So now we've gotten to at least one of the words in the title. So the idea of kernels. So the insight about all these learning algorithms is that many algorithms only care about dot products. So dot products kind of think conceptually as a way of codifying similarity or dissimilarity between two vectors. And the idea of a kernel is that instead of defining this explicit representation of a feature in a very high dimensional space, we're just going to define the function that takes two vectors and spits out a real number that is the dot product. So the prototypical example of this is the Gaussian kernel, what's typically called, for reasons I'm not really sure, the radial basis function, but you can see it looks basically like a scaled Gaussian distribution. So this is a valid inner product in some very high dimensional space. And the key here is that we didn't have to explicitly materialize phi of x, our feature map, in order to evaluate this dot product. So you give me an x and y, and I assert that this is actually a dot product of a very high dimensional space, but I didn't have to actually enumerate from x1 to x infinity, and I can still get a dot product out. So this is a picture of what it might look like. I think we've all seen Gaussian distributions, so I don't know. Okay, so now the problem here is how do we learn with kernels? So we've kind of postulated this very nice object. How do we learn with them? Before on the top, we basically just learned a linear model, and we solved this problem in D dimensions. And now after, it turns out you can actually solve this problem, which is the optimization problem in n. So n is the number of data points, and if you do this, so you form this thing called a kernel matrix, where you take all pairs of these points and you evaluate the kernel function on them, and you form this giant matrix. And if you solve this problem, it turns out, for reasons that are not completely obvious, but it's a very, very elegant theorem in functional analysis that basically says that these two are equivalent. It's very cool. But there's one caveat here, which is that the bottom problem is a decision variable in n. So, big data, what if n is really big? Okay, so that's the problem that this paper is trying to solve. Okay, so we have this beautiful, elegant mathematical way of taking this, this problem in D dimensions and going to n, but now we have to solve this problem, and n can get really big. In particular, it takes about O of n cubed operations to solve the kernel least squares problem. So the paper's main idea is that, okay, well, we should go back to a lower dimensional representation, but we're going to use random Fourier features. So there's this another really cool theorem in functional analysis that basically says if I take a kernel and then I take its Fourier transform, you don't have to remember what that is, but you use some integral, you integrate that kernel against some basic complex exponential. The thing that comes out is actually a valid probability distribution on RD. So we can take the Fourier transform, and out comes a probability distribution, which means that we can sample from it. And in particular, in the Gaussian case, when you take the Fourier transform of a Gaussian, you might remember from undergrad, you get another Gaussian back. So that's really cool, because then we can just sample from the Gaussian distribution, which we know how to do really well. So a little technical caveat is that this only works for translation invariant kernels, which basically means kernels where the inner product only depends on the distance between 2 points. And the Gaussian case, actually, you can see that that is the case. So there's a little slight technical restriction. So the way that this works is really, really neat. It's you take the Fourier transform. So by this, the first bullet point, I mean you do this analytically. Like you're not going to ask the computer to do this. So you get this probability distribution back, and you set D to be essentially linear in the number of dimensions of the ambient problem. So so I'm hiding some log factors, but the point is that D scales linearly in D. Epsilon is just some parameter, some little error tolerance you get for how good your approximation is. But you set D equals linear in the number of dimensions, and you just draw D samples from this distribution, and you form this random feature map that is basically you take each of these random vectors you drew, you take the thing you want to featureize, you project it on, you add a little offset, and then you take the cosine. So this is now your feature map. It's random, but it's very easy to evaluate, right? Like I can, on computer, I can sample Gaussian, I can sample uniform, and I can just take cosines. That seems really random, so let me just try to give some intuition for why that works. So by definition of Fourier transforms, it's basically what you have is that this distribution you get, if you sort of take this representation, which is just a complex exponential, and you take its expectation, you get out essentially the kernel. So what the trick then is that you need to realize that kernels are only real valued, and you can basically convert the top to the complex exponential form, which is hard to work with in computers. Like, I mean, it's kind of annoying. And you can turn it into cosines. And this equivalence is not immediate. It's not hard to show. It just requires you to use some trig identities, which I forgot all of them, but I just looked them up on Wikipedia. And so I wrote this blog post that if you're interested, you can it's not actually in the paper for how they go from here to here. They just say it's kind of obvious, but it requires a little bit of work. Huh? Yeah, I mean, okay, you're right. Euler and then some trig identities, which I forgot. It's basically that. Okay, so you get these cosines out, but this is only one scalar. And so remember, we have an expectation here. So what we want to do is we want to do this d times and take an average. So if you remember concentration inequalities or concentration of measure or basically law of large numbers, when you sample IID for some distribution, you take an average, you get increasingly close to the mean. And so basically we set that big D to be large enough so that we get a pretty good approximation of the kernel. Right? So you can imagine where that epsilon comes in. All right, so to kind of wrap it up here, how does this compare with doing just the sort of naive kernel formulation? So remember, we had a problem of size n, right? It's a number of data points. And we've shown a way to reduce that to a problem of size d, so linear in the dimension, hiding log factors. So when d is much smaller than n, and hopefully this is the case as n gets really big, then this is clearly a win, right? And it turns out you can also prove that this isn't just nonsense. You're actually doing a uniformly good approximation of this kernel over some space. So it's not just that any 2 points are well approximated. It's all the points in some set. This is the main technical contribution in the paper, but I don't have time to go into the proof. Okay, so the remaining question is does this actually work? So there's many ways to evaluate if this works. I think one of the ways that I was going to try to motivate whether it worked is to say that it's actually implemented in scikit-learn. So you can actually just import this guy and then just run it. So this is really cool because the authors didn't write this. People actually use this a lot, and so you can actually just try it. And here's just a picture of learning. On the left-hand side, we're going to learn a kernel SVM. And so this is a multi-class problem here. And on the left-hand side, we're not using this random feature formulation. We're just using kernels. And you can see all the decision boundaries there in different colors. And on the right-hand side, we basically use, or these people use the random feature formulation, and you essentially get the same thing. I mean, granted, this is a very contrived example, but the point is that this gives a very good approximation and is used actually quite widely in practice. So that's all I have, and I ran a little bit over time, but yeah, so that's it. Thanks. Yeah, sure, we can.
Also, you're speaking next year in March.
Oh, great. Okay. So if anyone wants to hear more about random Fourier features, raise your hand. Okay. Maybe we'll talk about that or something else.
No pressing questions? Then if not, then
Okay. Great. Thanks.
All right, and now it's Jason's turn. So Jason is a senior software engineer at Apple, as well as being an Apache Cassandra committer. He holds a master degree. Oh, I was not supposed to say that? Okay, everybody forget that. It's in his bio. He holds a master's degree in music composition, is searching for time to write a second string quartet, and he's also a national ping pong champion. So let's give it up for Jason.
Hi, everybody. Thanks for coming out. As mentioned, my name is Jason. I'm gainfully employed somewhere here in Silicon Valley, and I'm here tonight to talk about a topic that's very near and dear to my heart. Basically, gossip and using epidemic-style dissemination protocols for spreading information around a distributed database. As I mentioned, I'm a committer on the Apache Cassandra project. We use gossip in several different places, actually one primary place inside the application. And I've spent enough time debugging in production that I have a love-hate relationship with gossip systems in general, so I've had to get really down and dirty into the details. So the agenda for tonight is we'll first talk about the epidemic algorithms paper itself. That's the primary focus of this. Then we're going to do a very brief kind of literature overview that came out over the years after this paper was originally written, because it was written in the 1980s. Then I'm going to talk about two modern implementations of gossip systems, one being in Cassandra and the other being in Riak. And scuttlebutt and plumtree are the names of the papers that both systems have based their implementations on. So, to start off with, epidemic algorithms for replicated database maintenance. It's a industry research paper that came out of Xerox in the late 80s. I think it was 1988. And basically what they were trying to do is they had a bunch of databases spread across a bunch of different sites in both North America and Europe, and they were trying to make these databases converge. And they ran into some interesting problems. And they're also one of the first companies to start trying to do this. So first, let's talk a little bit about background, about where this whole system came from and what they were trying to do. Basically, there are two papers from the early 80s that Xerox wrote, one being Grapevine, which was a pure research kind of paper, and Clearinghouse. Basically, what Grapevine was a directory lookup service for systems, users, mail, and basically just distributed objects in general. And then Clearinghouse was the productization of that, which came out about a year or two later. And just as kind of a little brief historical prelude, interest, I thought we could talk about actually some of the statistics they had of running this thing in production with real customers paying to use it. So they had about 1,500 users, about 500 groups, 2,500 messages per day, 500 bytes each, max. And the peak load was about 150 messages per hour. Not per minute, not per second, per hour. And they're running it all on this bad boy. Actually, a cluster of 70 of these. This is the a Xerox Park Alto machine. And had 128K of main memory, a whole 5 megabytes of disk storage. And remember, this is the database they ran on this. And it could maintain 12 simultaneous connections. So I guess not so bad for the early 80s, but probably wouldn't scale up to modern needs, I'm probably guessing. So that's for the history. Now the epidemic algorithms paper that came out in the late 80s, where they start discussing some of the problems they ran into as they ran this in production and some of their solutions to those problems. So the contributions of the paper are to introduce some novel algorithms for converging the data to make sure that it's all are the same across all the different replicas they had worldwide. And it was the first real discussion of epidemic algorithms in, to be used in practice. So they talk about three primary algorithms. First, it's called direct mail, anti-entropy, and the last one is rumor mongering. Direct mail is as soon as one of the replicas gets an update, it just immediately floods the network and sends out that update to all the peers everywhere. Anti-entropy is basically a periodic exchange of data between two nodes. So if I'm a node, I would randomly select another node, we exchange data, and then reconcile any differences. The last one, rumor mongering, this is the basis of a gossip type kind of system. And it's all based off of the concept of epidemics out of like medical literature. So if you think of diseases, say like Ebola or other communicable diseases, it starts off with one person is infected, they spread it to another person, gets spread to another person, and so on and so on. In computer science, this is a good thing. Obviously, with health epidemics, it's typically not a good thing. So there's typically three states that a computer can be in with respect to gossip systems. It can be infective, which means I've got something that I want to share with the rest of the cluster. It can be susceptible, which means I don't have this update, but I'm willing to accept it and pass it along to the other nodes after I hear about it. And then removed. And that's, I've already gotten the update, but I don't want to broadcast it out anymore because I think the rest of the cluster already knows about this. And so let's actually just walk through a quick animation of how an epidemic would work. So let's say that there's this node at the top. It's got some piece of information it wants to share. Picks a random peer in the cluster and sends the update over there. And now they both know this piece of information. Now, on the next round, both nodes pick other random nodes in the other cluster to share this information with, and they share it. Now 4 nodes of the cluster have it. And on the next round, all 4 of those share with 4 more nodes, and they have it. So guess what happens now? Everyone starts sharing, and now the entire cluster knows this piece of information. So the interesting thing about this is that it all started with the node at the very top having it, and then it got spread out to the rest of the cluster. Not by broadcasting and flooding out the entire network, but by randomly picking peers and then each round keep broadcasting it around so that eventually everyone knows about it and sort of a log-in sort of a distribution in this case. And if one node goes down, that's okay because it's fault tolerant enough that if one node goes down, then another node would just broadcast that out to a node that should have gotten it a priori. So the motivations behind this paper are really they were trying to achieve consistency across all their databases. Should sound pretty familiar to anyone who runs databases these days. But they were running into some problems. As they were growing and building out more and more sites and more data keeps getting put into this database, they're running into problems where they had these nightly batch jobs that would try to reconcile data. And it wouldn't actually run before it was supposed to complete, or it would crash. They'd run into a bunch of problems with their internal messaging system. Basically, they would overload it. It would come down. They're sending because they had sites in both North America and Europe. They were essentially starting to bottleneck on the transatlantic cabling and how much data they could shove back and forth because they're trying to just compare every site with every other one pretty much. And so basically they were running into some big problems and they needed to fix these. And so as they were trying to pick out some ways of optimizing all their problems, basically they kind of figured out that they don't want to make any assumptions about guarantees from any underlying communications protocols. So either TCP or UDP, basically they're going to assume that this is the real world, things are going to break, packets are going to get lost. And the other novel things that they're using randomization to select peers, rather than having some strict static overlay of what nodes talk to what nodes and who's connected to what. They used a random selection of peers to exchange data. Yes?
How do all the peers know the process is complete?
The overall process of trying to reconcile every node against every other?
At what point does a node in the system stop trying to select random new nodes to send?
So the original system they started with was consisted of those two sort of algorithms. The direct mail, which is as soon as I get an update, I just broadcast it out and it's done. The other thing was this nightly batch job, essentially, of every node selecting a random other a node in the cluster, whether it be in the same data center or on another continent, and then just exchanging it like that. Beyond that, there was like no real God's eye view, if you will, of knowing that everything is done, except for perhaps if they had some centralized logging. But then again, this is the mid '80s, and I'm not sure how common all this was. So I don't have a great answer, and also I think in the mid '80s I was still just eating Captain Crunch and watching Sunday cartoons. So, Jordan. So the question was, how did the people who were actually running and monitoring the system, how did they know that their jobs actually did run to completion? And my answer was, I'm not really sure that, because they don't talk about that in the paper so much, but we can extrapolate some details. Yes?
How does a node transition to remove?
How does a node transition to removed? So that's part of the epidemic, the rumor mongering algorithm, which I'm going to get to in a little bit. The short story is there's a lot of different ways that they would try to calculate this by if a peer had already had it or whatnot. They would get a response and then choose not to send it on and forward it. But I'm actually not going to go too far into those details since it's. I also want to save time to talk about modern implementations of these systems. So there's three main sections of the paper. One is the first section is the algorithms, which I've kind of started to highlight. The second part deals with distributed deletes, and the third part deals with non-uniform spatial distribution. I'm not going to talk so much about the sections 2 and 3 because I want to save time for the latter implementations, but I'll just touch briefly on those because those are very pertinent to a lot of what we do as practitioners on a day-to-day basis. So first up, algorithms. So the kind of system that they're running is basically a distributed key value store, where the value is a two-tuple of a value and a timestamp. And on updates, when you update a given key, basically they would choose a higher timestamp. If this sounds anything like any kind of databases that somebody might be running in production, it very much sounds like a Cassandra style last writer wins kind of system. So talking about timestamps though, there's an interesting caveat in the paper. And I'll quote it explicitly. One hopes that the timestamps will be approximately the Greenwich Mean Time. If not, the algorithms work formally, but not practically. Yeah. So, direct mail. As I mentioned, this is when a given node or site, as they refer to them in the paper, gets an update, just broadcasts it out to the rest of the cluster. However, as practitioners, we know that failures happen, and the durable messaging queues fill up, and we saturate network stacks and queues or packets get dropped. So, and furthermore, we might not know all the peers we need to broadcast this information to, so therefore we don't get 100% coverage whenever an update does occur. So that's why we introduced the two other forms of reconciliation. First one is the anti-entropy. It's a periodic comparison of one site to another, or one database to another. And it's basically a full data set transfer. Now, of course, since at max I had 5 megabytes of disk space, it's probably not transferring a whole lot, but given the actual network bandwidth they probably had back in the mid-'80s, apparently that was quite a lot. So on top of this, there's three different modes or styles with which to reconcile data. The first one is called push, which means basically I select a random peer and I push all my data to that peer, and that peer reconciles any differences. The second one is pull, where I ask a peer for some data and they ship it all to me and I reconcile any differences locally. And then the third one, I'm sure you can guess it, is probably push-pull. Basically, I push all the data to a peer and they send it all to me, and then we each individually resolve any differences locally. This is also a very simple form of an epidemic. It doesn't spread far. It does not spread beyond those first two nodes, but it's basically one node contacting another and doing the comparisons. So, because this was doing a full data set transfer and especially on those transatlantic links, they were running into some problems, bandwidth problems. So being practitioners that they were, they came up with a few optimizations. The first one was that they did a full checksum at each site. They maintained a full checksum at each site, and when an anti-entropy session began, they would first exchange these checksums, and if the checksums were the same, great, we don't need to exchange any data. However, if they were different, we'd have to do that full data set exchange and then do the full set reconciliation. So there's a couple of problems with that. Like, how do we know when like if two nodes are in a cluster and one gets an update, but the other doesn't yet, and all the other data is the same, one checksum is obviously going to be different, but only based on one difference. So what they discovered was that if the anti-entropy session starts and there's only one difference, they would still end up exchanging all this different data. So they really started, so they came up with this idea of a time window that maintains the list of the most recent updates. And what they would do first is exchange these updates, then exchange the checksums, then do the full data set transfer if they needed. Well, that then brings up another problem of what happens, of how do you actually define that time epoch? How is this midnight or is this every 10 minutes bounded, so that every 10 minutes? But then how do we know that everyone's clocks are in sync, because clocks aren't in sync? So the third optimization, basically they maintain an inverted index of all the updates by the timestamp, and then on these anti-entropy sessions, they essentially just walk backwards through this in reverse, compare all the checksums, and then exchange any data. Then as soon as the checksums are the same, then they know they can stop. So this was the primary ways of optimizing the anti-entropy part. Then they also introduced the rumor mongering model. And to go back to those initial three states, susceptible, infective, and removed, the real question is, I think the gentleman over here asked, is how do you know when to stop sending those updates? As I mentioned, I'm actually not going to step through that. There's actually some pieces in the paper that talk a lot about it. If you're really interested, I advise going to read that, but I think there's some more interesting parts of the paper to dissect before diving into that. So, how do we define what is a good epidemic? They came up with this new algorithm. How do they know what's good? How are we measuring it? So they came up with these 3 points: residue, traffic, and delay. Residue is, once I start gossiping out a given update with the rest of the cluster, how many nodes, when we finally choose to stop gossiping that, how many nodes have not received that update? And that's what they refer to as the residue. Obviously, you want that as far down to 0 as you can, but it doesn't always happen. Traffic is the amount of messages that are actually exchanged between nodes in order to propagate a given update through the entire cluster. And delay is the average wall clock time that it takes to get from one node to another, both the average and the max. And once again, this is dependent upon wall clock times and trying to and making the assumption that they're somehow globally synced or reasonably well synced across the cluster. So, rumor mongering and anti-entropy. We're just going to talk about this very quickly. Over for now. I'm moving on to the second section, distributed deletes. Working in modern NoSQL databases, is a problem we have to deal with is how to actually get rid of data. So they came up with this idea called the death certificate, and this is very equivalent. It's the modern equivalent in Cassandra, and I believe in Riak as well, is called the tombstone. And basically, it's the difference between a logical delete and a physical delete. And the reason why we'd choose to do, and basically what it is a logical delete. So instead of actually deleting data immediately, we essentially put in a marker or some metadata that a piece of data has been deleted. And the reason why we would choose to do that is when we're actually going to reconcile two different nodes, if a write came into a node and it then wanted to share that with a peer, and the and it never got over there. Say some packet got dropped or some network partition. Then when we go to reconcile these two nodes, just node A's data would go over to node B, and they're reconciled. However, if node B, if node A and node B got the data, but then node B got a delete, and it immediately removed the data, it's no longer there, then when the two nodes go to reconcile, how do we know what's actually happened? Because B actually deleted the data because there's a more recent mutation to that. But then in that case, A's data will actually just get sent over to B, and you've essentially resurrected that data. So that's why we would choose to have a logical delete. And the death certificates in the paper, these get propagated just like regular writes. And each node keeps around these death certificates for a fixed length of time at all sites. And then after some time, be it 30 days, 40 days, or whatever, everything kind of gets garbage collected locally on each node. However, they also came up with the idea of a dormant death certificate. And clearly these guys were practitioners because they realized that, yeah, after we deleted all these death certificates from all these nodes, we still got some resurrected data. So what the hell, why don't we just, on a few nodes, keep around those death certificates for just a little bit more amount of time? Because it could be that we still didn't resolve everything in time before we deleted all the tombstones, and but some nodes still had data and it got resurrected. So what they would do is these dormant death certificates would live on for some period of time longer than the original death certificate, and it would essentially reawaken when a peer node started broadcasting out this data that should be removed. So these dormant death certificates weren't propagated around via anti-entropy or rumor mongering, because it just kind of lived on a few nodes for that just in case time. And then after it did become reactivated, it would just spread around like a normal tombstone. As I mentioned, Cassandra has the notion of tombstones. We keep it around for a limited amount of time. That's typically user configurable. But then we don't have anything like the dormant death certificate or some given node just keeping these things around for an extra bit of time. But clearly, the authors of the Xerox system probably ran into this problem, and that's why they bothered to create it and keep it around even longer. So the last section of the paper talks about non-uniform spatial distributions. I'm going to spend one slide on this, and basically the problem that they ran into is that with these anti-entropy jobs, these nightly batch jobs that would run, they would basically flood the network connection between transatlantic sites, and so what they wanted to do was optimize their usage of the transatlantic packets. So they would just favor doing anti-entropy sessions with local data center nodes or nodes that are closer to it, and then only selecting a few nodes to actually exchange across the Atlantic. And in the paper, it's got a bunch of simulations and results that are interesting, but I'm not going to cover that here. So to kind of recap this paper, first they talked about the gossip algorithms that were pretty novel back in the mid-'80s, late '80s. Distributed deletes, which was a problem they clearly ran into. And the other thing that I found really interesting about this paper is that if you squint your eyes really hard, it really looks like basically modern NoSQL databases. Yes, interesting comment from the galleries. So now I'm going to do a very quick I'll mention of some papers that came out in between the Xerox paper from the late '80s until the modern days. So bimodal multicast basically is a paper that kind of codifies the notion of having a sort of two components of a gossip system. One part which just, as soon as an update happens, it kind of broadcasts it out through a system. And then a second part, which is like the anti-entropy, which then basically periodically comes along and cleans up all the data that didn't get reconciled in the first place. The swim paper came out around 2000, 2004. It was actually covered in a talk here, maybe I think 12 months ago, by Armin. Very interesting talk. I recommend you check it out if you're interested. Peer sampling service. So in the early 2000s, academics were really interested in this whole peer-to-peer kind of systems that were coming out, because now we had really finally big scale, like tens of thousands of machines. And the thing they realized is that you really can't connect tens or 20,000 machines together in one big ass mesh. So they came up with this idea of creating partial views of an entire cluster. So if you can know like the rough overall size of a cluster, which is kind of a loose idea to begin with, then you can take like some small subset of that cluster, which you kind of comprises your view of it. And your view will then overlap another node's view of the cluster, which then overlaps with everyone else's view. And essentially you get this kind of a distributed mesh of how much of the cluster you know. That way you don't need to know the entire membership of the cluster, but that when you actually do start to broadcast gossip data around, eventually it will be picked up by all the other peers in the cluster. And the last one is a gossip-style failure detection service, which I have a lot of feelings about failure detection schemas, but this one uses gossip to essentially disseminate heartbeats to let other peers in the cluster know that a given node is up or alive. So let's finally dig into how some of these things are used in modern systems. In Cassandra, we have a system that's based on a paper called Scuttlebutt, and in Riak, it's based on part of the system is based on a paper called Plumtree, and they're both written around the same time in around 2007, 2008. I'm going to start with Cassandra first. So the paper that we base it on is called Efficient Reconciliation and Flow Control for Anti-Entropy Protocols. It's kind of a mouthful, but at the end of the day, it's efficient reconciliation, so it's reconciling data, and flow control, meaning controlling the amount of data going back and forth, for anti-entropy protocols. And anti-entropy protocol here maps pretty much one-to-one with the Xerox paper of essentially two nodes exchanging data and reconciling them independently. And this was written by an academic, Robert Van Renesse, in 2008. Paper's nickname is Scuttlebutt. And inside of Cassandra, we use this for exchanging metadata about nodes. So what nodes are in the cluster and what types of data they're actually owning at this point. So anti-entropy, as we've already talked about, it's a merge operation that's periodic and it uses a randomly selected peer. So pretty much just like the Xerox paper. There's basically one key data structure in this whole thing. So each node maintains a metadata map. And it's essentially a key to a value inversion. In this case, a version is an infinite ordered set of version numbers. Basically, it's just a monotonically incrementing integer. And there's one update at a time per node per key. And the way that we determine what is the most current value for a given key is that we just look at that version for the value, and we just select that one. And the way that the reconciliation works is that we exchange a digest. It's a two-tuple of the peer and the max version that it has. They exchange the deltas, and then they'll exchange any differences that occur. And I've got an animation that shows this. So I've got three nodes, A, B, and C, and they all have some metadata that they know about their peers. So node A knows that the highest version of node A, which is itself, is some integer version of 42. It knows that the highest version of B is 14 and the highest version of C is 37. I just picked these numbers arbitrarily for examples. B pretty much matches with A except for its known value of C, which it thinks is 38. Then over here on C, I'll just stand over here. The highest version it knows of node A is 40, and so on. So the real differences we have here are A doesn't have the highest version of C's value, which is 38. Similarly, C doesn't know about A's largest version, which is 42. So let's imagine that some anti-entropy session based on the Scuttlebutt starts between nodes A and C. First, A will send a digest over to node C of basically what it has. Then C sends back an ACK, and it sends the updated data that it has based upon the digest it got from A, as well as it requests any data that it needs because it knows it has not current data. And what that looks like is C will send over the data associated for 38, and it says, hey, I need all the data starting from version 40. And then A, when it receives an ACT, updates its information about C. And then the response from A, it's an ACT 2 message, and it sends the updates, which is basically, hey, here's all my updated data up to version 42, and C updates itself. And so at the end of this anti-entropy session, now A and C are more or less in sync. And in Cassandra, we use this basically for membership, so knowing who else is in the cluster. Ownership, knowing what nodes own what part of the distributed hash table, as well as other random bits of metadata about the peer nodes. So like what data center it's in, what rack it's in, the version of Cassandra that it's running, and a few other things that aren't so interesting. So I'm talking about Riak. So part of it is based upon a paper called Epidemic Broadcast Trees, written by some of our friends in Portugal in 2007. The nickname of the paper is plumtree, and it's used a good chunk of it for cluster metadata, so similar to Cassandra's exchanging data about information about nodes. So plumtree is sort of the rumor mongering style of disseminating data in this kind of epidemic style I've been talking about. And it does this via spanning trees. And the architecture is that it's based upon some underlying peer sampling service, as I kind of mentioned, is one of the earlier papers. And plumtree really deals with tree construction and tree repair. So construction, because these are dynamically built trees, not anything static. They get generated at runtime, and then they can get constructed at runtime when messages are actually sent, and then repairing trees when either nodes fail or when messages get dropped and not delivered. And very briefly, if you can imagine these two systems, plumtree asks for all the peers from the sampling service, and the sampling service has a couple of callbacks into that to let plumtree know when nodes are up or down, so that plumtree can readjust and remove nodes or add nodes to its views. And in plumtree, there's essentially two lists. There's a set of eager push peers, as it's called in the paper, where and those are the nodes for which broadcasts occur. So meaning whenever an update occurs, we immediately broadcast all those peers. Then there's a second set called lazy push peers, and we use those for repairing the tree when failures occur. And got something of an animation to hopefully explain this. I'm not an artist, so please bear with my artwork in Keynote. So imagine a cluster of 5 nodes. And the thing about plumtree is that on initialization, so when it starts, it first calls into the peer sampling service to get a set of lists, a set of nodes for which it should broadcast messages to. And we put that into the eager list. For sake of simplicity, I've just I made these all to be rather symmetric, so that when one knows about nodes 2 and 4 in its eager list, node 2 and node 4 will also both know about node 1. Part of this is the underlying peer sampling service. Part of it is also plumtree. So and nothing starts off in the lazy set. So let's say that node 1 has a message that it wants to broadcast out to the rest of the cluster. It first looks at its eager set and broadcasts to nodes 2 and nodes 4. And when node 2 gets a message, it looks and says, the nodes in my set, in my eager set are 1 and 3. I'm not going to send the same message back to node 1, so I'll just send it to node 3. Similar for node 4. Once it gets that message from node 1, it looks into its eager set. It doesn't send it back to node 1, but we'll pass it off to node 5. Pretty straightforward so far. So what happens then when a given node gets a duplicate message? So in this case, when node 3 got that message, it looks up into its eager list for nodes 2 and 5. It's not going to send the message back to node 2 because that's who it got it from, but it's going to send it on down to node 5. However, node 5 already has this message. So because this is a tree, basically what we're going to do is node 5 is going to recognize that it got a duplicate. It's going to remove node 3 from its eager set and put it into its lazy set. and then send a message back to node 3 that's a prune message, meaning remove me from your eager set and put me into your lazy set. And a similar thing happens then when I went down here, when node 5 got that first message from node 4 and it sends it up to 3, a similar kind of removing from the eager set into the lazy set occurs. And so you end up with a tree. I'm not sure if everyone can see it down here, but a dynamically built tree that started at node 1, and then it fanned out to both nodes 2 and 4, and then those sent messages to 3 and 5. And so now this is sort of the tree that got dynamically built. So then the repair in plumtree. So this is basically when messages don't get delivered or there's a failure. So how do we actually detect this? So basically that lazy set that each node has, periodically it'll broadcast out to each node will broadcast out to one of its lazy peers an I have message. And basically what it does is it broadcasts out those message IDs that it receives, and it sends that over to the peer. And the peer will wait to get all those message IDs. And if it gets all those messages, great. It can send a response back to the original sender. However, if it never got those messages, meaning it never got those messages eagerly pushed to it, that means there must have been some kind of failure or some kind of delay that happened upstream of it. And then that there was some other node that was able to give us this information faster. So what we'll do is we'll send a graphed message over to the peer that sent the I have message. And so essentially we graph part of the tree together so that we can heal around either a delay or a failure of a node. And very briefly, so let's say I've got the same 5-node cluster. This is with the same built tree at the end of my last example. Let's say that node 4 fails or is somehow unavailable now. So in this case, a node 3 sends an I have message for some set of message IDs over to node 5. Node 5 decides, well, I haven't gotten that message yet because node 4 is the one that was supposed to send it to me because I'm in its eager push set. So then node 5 sends a graphed message back to node 3, and it moves node 3 back into its eager set, and node 3 moves node 5 back into its eager set. So essentially now we've healed the tree because whenever 3 gets a message, it'll immediately send that on to 5, and we've healed around the failure of node 4. So one last interesting caveat in this paper that's kind of interesting. The authors of the paper basically kind of envisioned plum tree as being one tree for an entire cluster. As practitioners, that kind of doesn't work so well because you can get into problems of trying to send, knowing who the root node of this entire tree is, and then trying to send a message over to that so it can get broadcast out through the rest of the cluster through that dynamically built tree. So there's a small section in the paper that talks about sender-based versus shared trees. A shared tree is the one I just described, where there's one tree for the entire cluster. A sender-based tree is where every node in the cluster has its own tree rooted at itself. And of course, those are dynamically built according to message propagation. And this seems to be the more preferred approach for practitioners, I think. Then finally, how this is actually used in Riak is that it's part of a two-part gossip system. The top one, plumtree being the broadcast component, and there's a anti-HTTP component underneath it. So similar to that bimodal multicast paper that I referenced earlier. And we're actually using logical clocks for tracking if a node's got a message delivered to it or not. Then, so finally, after all this, the takeaways that I'd like to share with is that convergence is hard, and distributed deletes are even harder. And epidemic algorithms help to mitigate a failure of either packets getting dropped, network partitions by being fault tolerant and resilient, but at the price of eventual consistency. And there's a bunch of modern databases that use this technique, and showed a couple this evening, both in Cassandra and Riak. And with that, thank you, and I'll open it up for questions. Yes, Jordan. Oh. So the question was, did the authors use the SRI model for determining what nodes to talk to, the rate at which they communicate, and so on? I'm not familiar with the SRI model, so maybe if you can explain it briefly, I can see if I can. SIR, sorry.
Susceptible infected recovery.
Oh.
Yeah. So that's like
Yeah.
the model they used was so he
Yeah.
said for epidemiology, you assume that you have these two rates, which is like the recovery rate and the infection rate, and those are just two parameters based on an actual disease would be the virality
Yeah.
of the disease.
Yeah.
You can figure out whether or not you're like over the epidemic threshold or compute a lot of things based on.
Yeah. So they had as far as the how often to try to answer this best I can. As far as how often to broadcast to start these epidemics, it's basically as soon as a given node got an update. Then when to actually end it, to figure out when you're actually over that hump. The paper had about 4 or 5 different variants of things they tried. That's all in the paper. Yeah. Mr. West?
Am I right in understanding that since scuttlebutt uses a single integer for a logical clock, that nodes can only update information about themselves in that model?
So the question was, since scuttlebutt uses an integer, is it right to assume that nodes only update information about themselves? And the answer is yes. In Cassandra, we do have a little backdoor hack for, in very limited and very unique circumstances where another node can increment another one's clock. However, that's only in the case of when a node is being removed from a cluster and you can't bring it up and you've just got to shoot it in the head. And then in other cases when you've already shot it in the head and you really need to shoot it head in again. Yeah, basically it's a function. It's a function called unsafe assassinate endpoint. The name should really just tell you everything.
It's not unsafe anymore. But,
No comment.
You're sure that you can generate another unique ID from another node and it's safe, but otherwise,
Correct.
would it work? The question was, would it work with a different logical clock?
The question is, would it work with a different logical clock? If you're, absolutely. I assume you could just use something like a version vector and it'd be fine. Yeah, I don't see any reason why it couldn't work.
And my last question is, do you see the two algorithms that you presented in the databases as like competing? If so, what do you prefer? Do you see them as complementary?
The question was, do I see the two algorithms I presented? I'm assuming you're talking about the scuttlebutt and the plumtree as being complementary or not complementary. I think they can work in a complementary way because a plumtree is really a broadcast primitive, and scuttlebutt is more anti-entropy. And so if you put those together in a system that, like the bimodal multicast, basically has both of those components, I think they could probably work reasonably well together.
You had a question, right? Oh, yeah. Are there systems sort of between Cassandra and what this paper was written that use these techniques?
So the question was, are there systems in between Cassandra and the Xerox paper from the 80s that use these kinds of systems? I'm going to assume the answer is yes, but unfortunately I don't know any off the top of my head. Dynamo? Yeah. Which of course Cassandra and Riak are based on.
Paul, you had a question?
Yeah, both my questions are for me. Well, I know. Which of these two schemes would scale the best? And can you say something about scalability? Trees tend to be more fragile the further you go out to the leaf when the leaves are a long way away.
So the question was, which of these two do I think scales better? I think they both have their independent merits, but I think once you get up into the scale like 10 to 20,000 nodes, I don't have any evidence for either one being better. I kind of think my personal opinion, my professional opinion is that I think we kind of need both. Because with anti-entropy, essentially you have to select a random peer, or you have to select somebody to exchange data with. Once you get into the land of 10,000 nodes, even if you cycled through all 10,000, and even if you did that every second, you're still 10,000 seconds later. With broadcast, in the sense of like a plumtree or something similar, it is a dynamically built tree, and so you had to have all these reconciliation mechanisms to repair the tree when failures do occur, but then you do get a much faster broadcast of that. So you can hopefully get the vast majority of things converged quicker, but then but I still think you need some kind of essentially backup kind of system to bring the rest of the system into reconciliation. So I kind of imagine it as kind of a mix of both.
Last questions about Mini. First one is like, why did we start with epidemics and now we're into gossip? Is it like just because it's like gossip is like the fancy word now for epidemics?
Interesting. So the question is, why did the nomenclature switch from epidemic to gossip? I actually don't know. That's an excellent question. I believe most of the literature typically does tend to refer to it as gossip. I think even in the Xerox paper, the Demers paper does mention gossip, but they tend to use the rumor mongering notion more than gossip.
And scuttlebutt, but scuttlebutt, why that name?
Oh,
It's a nickname for gossip around the water cooler.
yeah,
Scuttlebutt? Oh,
Yeah.
oh, so you said okay.
yeah. It's kind of a more informal word of describing gossip.
We're just going to comment about the earlier question about other systems that use gossip. Yeah, sorry. And I will say there is some interesting work that was done. So what's an interesting observation is out of that list of papers that was presented earlier, at least 3 of those were Cornell, and they're all in the distributed systems group, of Ken Berman and Robert Van Renesse. And there is an interesting system that never implemented gossip, but proposed a design for it called Quicksilver, which is like a generic distributed objects programming framework that's supposed to have pluggable backends. So you're supposed to say like, well, I want to have a gossip backend, or I want to have like a consistent hash ring style quorum system, or I want to have state machine replication. So, which is also Ken Berman's group at Cornell. So if you stay around the Robert Van Renesse, Berman kind of Fred Schneider kind of line of research, there's a variety of work around gossip. So.
I guess technically, right, like LimeWire and all that work. Bunch of scales. Yeah.
Based on pure exchange. Yeah, so all the Nutella-based ones. So Nutella, which
Yeah.
was the like first post-Napster peer-to-peer, that's gossip, and LimeWire also was the Nutella protocol, so it's also gossip. And then BitTorrent has a bunch of distribution modes, but one of them is called peer exchange, and that's gossip.
Yes. Thank you for bringing up the Nutella example as well. So I've primarily been exploring gossip in the sense of distributed databases, but yeah, there's other application models certainly for using this, and the file sharing Nutella example is perfect.
So I have a question.
Sure.
What do you see the future like? Now that we have 35 years of experience, or 30, some number of experience,
Sure.
all that we know now, all the wisdom we've gained, all the things that people behind me have talked about, where do you see the future of distributed databases?
I just got trolled hard.
Where do you see the future of gossip in distributed data? Let's make it a little bit more fair.
Being rewritten as we speak, is that a fair answer? Where do I see the future of gossip? So I really liked what the folks in the Riak database did. I think that will scale out to a large amount of clusters, to a large amount of nodes. Similar things are happening in the Cassandra space. I think this style of system will definitely help for certain use cases. So I don't know if I'm not sure if this style of gossip necessarily works for just every update, like every kind of write that a database would get. I'm not sure that this is the right model. However, for things that don't change very much but are pretty important, like knowing who's in the rest of the cluster, what part of the distributed hash table do they own, these kinds of things which are more vital to the running of a cluster, I think this kind of system will help out very well with. And there's probably some other use cases that are in the middle, things that can probably have a reasonable update rate. But if you're throwing 100,000 writes at a cluster, I don't think this is the kind of system to actually make that replication happen. Jordan.
I've talked to you about this a lot, so I'm going to lead you a bit. But where do you see systems like hyperview playing a role versus, and can you explain what's different about that versus what we have?
So the question is, how would systems like hyperview play a role in?
You didn't mention that. How would peer sampling services with a partial view?
I was going to explain hyperview. So the real question is, how would systems that make use of a peer sampling service really play out into this? So as I mentioned earlier, with a peer sampling service, you essentially maintain a restricted view of the entire cluster. So instead of needing to know about all 10,000 nodes to communicate with, you only communicate with some limited subset. I think that's really important as you get into massive size clusters like upwards of 10,000 nodes, because trying to keep 10,000 connections open to 10,000 other nodes is a little bit problematic, and especially in the case of Cassandra, where we keep an open thread for every connection, it's even more of an efficiency problem. I mean, it's something that's actively being addressed in the Cassandra community. But I think if we can make these things more efficient by having smarter algorithms behind them of choosing how we share data around the cluster, I think this could help out a lot and make it more efficient.
Okay, question over there. That's enough.
Can you say more about some of the Cassandra-specific changes that are being proposed?
If you come to the Cassandra Summit in about 3 weeks, you'll hear a whole lot. By the way, I'm also giving that talk. Because you work at a certain company that may allow you to have certain access to this kind of information.
Also,
But
go to
who
the bar,
knows?
And then we can just, after the thing is recording. So yes.
Look at the Apache Jira.
Yeah.
Actually, there are some open tickets in the Apache Jira, some of which deal with failure detectors, some of which deal with a more strongly consistent membership in Cassandra.
So we normally tend to go to a bar. We have selected a new bar that is in the corner of this block. So if whoever wants to go, we can just thank Jason and talk to him.
Thank you very much.